Well, good evening and a warm welcome, really a heartfelt welcome to our pre-Spark meetup on the eve of the third Spark Summit here in Dublin, the beautiful city of Dublin. How many of you are from Dublin? Nobody? My name is Jules Damji, and I'm the Spark community advocate and developer advocate for Databricks, and I'm going to be your host today. I'm truly heartened to see so many of you actually are here for the Spark meetup. This is our 11th Spark Summit, and it's actually a momentous occasion for Spark community in general to have reached its 11th Spark Summit today. And so I'm really delighted to see so many of you over here for the meetup as well. And for those of you who actually crossed the oceans and crossed the overland, thank you for coming. And it's people like you who actually have contributed to Spark by either advocating it or either adopting it for your enterprises or just coming to this community meetups and giving talks in your own capacity. So I really appreciate that. And as of this morning, I checked that it's because of people like you. We have 625 Spark meetups globally, comprising of 430,000 members, 625 Apache Spark meetup groups around the world, and 435,000 people. That's phenomenal just in a matter of years. So give yourself a good hand because it's people like you who are actually helping us to grow Spark to the moment where it is today. So in your very special ways, you are actually contributing to the momentum of Spark, so keep the spirits high, and I hope you actually have a good meetup. Now, before we actually get into the meetup today, I have a couple of announcements for those of you who were late here. We're going to be having 2 birds of feather session tomorrow around lunchtime. There'll be some tables with the signage on it. One is the meetup, Spark Meetup Apache Organizers Meetup hosted by me and Jayzak and JP Perrin. I don't know if they are here today. So bring up your questions, and if you have rough feathers to ruffle, tell us how we can actually make these meetups internationally so we can actually all collaborate together. The second BOF is going to be about Apache Spark and Kubernetes. As you guys know, Kubernetes is really taken off. So is Spark, so it actually makes sense to have that. And then finally, we're going to have a Women in Big Data lunch on the 26th, so check your schedule. Please come and support all these enterprising women who are actually making a huge difference and dent in the world of technology. And then finally, our local guy, Ronald Tish. Are you here, Ronald? Yeah. The Dublin Apache Spark meetup is going to have a meetup as well on October the 26th at Nitro at 6 p.m. So if you have any questions about the Apache Spark meetup Dublin, talk to Ronald. He's right here. Now, to kick off today's meetup, we have our first speaker from Databricks called Tim Hunter. And many of you actually have worked with Spark. Many of you actually have also heard about TensorFlow. And today, if you go to any of the Spark meetups or any of the big data conferences, invariably, almost you'll have a fully crowded section on deep learning and AI and TensorFlow in particular. And Tim is a veteran to Spark. He has been contributing to MLlib since Apache Spark, or before Apache Spark. It was 0.2.0 at MLlib at UC Berkeley AmpLab, where he actually received his PhD, and he has been feverishly contributing to that particular project. He is also the co-author of Deep Learning Pipelines as well as GraphFriends, and he's a creator of TensorFrames. And today he's going to tell us how do you actually combine those data frames and TensorFrames to use Apache with Apache Spark and TensorFlow. So without any further ado, please welcome Tim Hunter, my fellow from Databricks.
Thank you, Jules. Thank you, Jules. Welcome everybody, and today it's my pleasure to talk about one of the ways in which you can integrate TensorFlow and Apache Spark, but also I think this aims at being a more general conversation about how you can do distributed numerical computing in a simple manner. So, okay, now I'm blushing after everything that Jules said, so I'll skip this slide. Today I would like to talk with you about how you can advance the state of numerical computing using modern technologies like Spark, and how also it helps us develop some new algorithms and allow us to get more performance without having to go down to really some low-level details. So when you look at the So when you look at the state of numerical computing, and also when you look at Spark, you see really two different worlds. Because on one side, when you're used to using Spark as an ETL tool for doing data transform, well, usually these transforms are very intensive in data. So they move a lot of data around, and they don't necessarily use a lot of computing power. And also the data that they move around tends to be highly structured. It is strings, it is arrays, it is objects. So it is usually a different paradigm from what you expect from algorithms. So when you think about the algorithm that we all love, such as logistic regression or machine learning, or even some other algorithms outside machine learning, then these algorithms tend to work on very simple types, numbers. They usually don't deal with string, they don't deal with objects. And usually, though, if you look at one of these pipelines that contains some numerical algorithms, these algorithms tend to be one of the bottlenecks in which a lot of the time gets spent because of all the number crunching that needs to happen. So really, it makes sense to try to optimize these bottlenecks and let data scientists and scientists get faster results and also run more experimentation in this way. So here, one of the questions I would like to talk with you about is how can we run these numerical algorithms faster without compromising the simplicity and the ease of use that we have with Spark, and how we can integrate easily these algorithms with the rest of the ecosystem of Spark that includes all the nice tools that we are used to using, such as Spark SQL, the graph processing libraries, and so on. So if you're a data scientist these days, and if you want to have more computing power, really you have two choices these days. Either you get better hardware or you get more hardware. So if you want to get better hardware, typically you ask your boss, for example, to upgrade your desktop into a fancy gaming machine, for example, and try to convince him it is not just for playing games. If then you have a lot of time on your hand, then you start to implement your algorithms into specific hardware, such as GPUs. And if you are a wealthy company in the Silicon Valley, then of course you go beyond that. You build your own chip to solve the problem you want to do. But this is usually out of reach for most of us. So the other option is, instead of having more fancy computers, is to have more of them. And this is really where Spark shines. So using Spark, you can distribute your workload on hundreds or thousands or even tens of thousands of machines. But then you have to deal with different problems, because in this case, it is very typical that one of the computers out of all of them will be failing somewhere. And if you look at these very different trends are also reflected in the kind of programming environments that they offer. So if you look in the case of more specialized hardware, such as GPUs, then you'll have some very low-level libraries, such as CUDA, that allow you to directly interact with the hardware. And then on top of that, a number of layers have been built, such as Torch, PyTorch, TensorFlow, NNTK, and so on. CNTK, Caffe, Theano, and a lot of others for doing deep learning. And if you have, on the other side, if you want to deal with a lot of machines, then the programming model is usually very different. And this is really the model followed by Spark and Mahout. And so today's talk is really trying to see how we can leverage these two trends together, and seeing how they converge together these days. Because on one side, all the framework that we're designing for one machine, one very efficient machine, now they want to be able to actually go faster by distributing some of their workload across multiple machines or across multiple GPUs. And then that brings some of the problem that we see in Spark. And conversely, Spark and MLlib in particular wants to be able to leverage all the advances that have been done in the hardware. So I will talk about one of the ways in which you can integrate Spark and TensorFlow, so two of the most popular packages in display that we all love. So what are the kind of problems that we need to deal with if we try to leverage better hardware? Well, if you look at what is happening with the hardware, you notice that now the processor speed simply cannot keep up with the memory and the network. So that means accessing the processor and moving data to the processor is becoming the new bottleneck for a lot of these systems. And this was dealt with in part in Spark by Project Tensor. in which in which using some heuristics, some computer code gets generated just in time to try to leverage the underlying hardware and to be able to access more efficiently the memory. But parallel tenston doesn't help you in the case of numerical computing because it was really designed for the SQL environment with these objects, with these arrays, with these structures. And it doesn't really help you when the problem is numerical, and when the problem consists usually of big, dense arrays of numbers. So that's why we need to go beyond that if we want to use GPUs and more accelerated hardware. So everybody probably at this point heard about GPUs and why they are so good for doing numerical computing. So these days, actually, they're not even called GPUs. They're called general purpose graphics processing units. And why are they so good compared to a processor? So they are not as good for doing branching and the computation with the main memory. However, if you know how to program them correctly, they have a very high memory bandwidth and very high peak throughput in terms of number of operations per second. And this is why they can shine in these numerical settings. So of course, they're really hard to program. And this is why most of the users don't directly interact with the hardware, but use some high-level libraries. And Google TensorFlow is probably one of the most popular of all of them for doing deep learning. But actually, Google TensorFlow is something that can be used beyond simply artificial intelligence and neural networks, because it describes itself actually as a machine intelligence library. So it's popular for deep learning, but it also has other primitives that you need if you want to do some more general calculations. Because if you want to do matrix multiplications, if you want to do other reduction operations, sum, means, and also all the transcendentals, they're all implemented inside TensorFlow. So you can use them for instead of writing your custom BLAST code, for example. And on top of that, it has, like a lot of deep learning libraries, it has two interfaces, one in C++ and one in Python, with some other languages now being supported. So what does TensorFlow provide as an environment for doing numerical computing? So it allows you to describe computations as a graph of transformations. So you start, for example, from some inputs. And here, for example, let's say it's two numbers, two integers. And then it lets you describe all the computation you do and then produce a result. And if you want to execute it, you open a session, which will then talk to the hardware, communicate the numbers for the input, and then it will return to you the output, here, Z. So when you look at something like that, that should remind you a bit of what Spark is doing. And we can actually leverage these libraries and this kind of API inside Spark. So the way it works is that you can consider each of the rows inside a data frame as being something that you're going to inject into TensorFlow, and then it will return to your result. So here, this graph of computation, of numerical computation, is simply a function that you can send and use to transform data frames inside Spark. So here, if you were to use it with some inputs x and y's, then it would produce a new column of a data frame containing the result of these computations here. And actually, let's see what it looks like in practice. So here I have a tiny Databricks notebooks that contains a small data frame. And let's display it. So you see here I have a small data frame containing some numbers, x and y's. And I'm going to write, and I'm going to import some libraries. So this is all Python code here. And in order to communicate between Spark and TensorFlow, I need to tell TensorFlow what kind of input it is going to get from Spark. And this is what this row object here corresponds to. So if I run them here, I see that TensorFlow is going to see a tensor, which is a numerical type, which is a scalar of size of 64 bits, so a long integer. Then I can describe in TensorFlow some of the computation I'm going to do. So here I'm going to do a simple transform, and I'm going to name the output out here. And then what I can do is take my data frame, and for each of the rows, I can map the content of this data frame using the transform I just described above here. And now you see I'm going to have an extra column out that is being added, and everything is lazy so far. Nothing has happened. So now Spark knows that it needs to apply this numerical transform on the rows, and it is going to use TensorFlow under the hood for doing that. So if I were to execute it, it is going to do what it's supposed to do, yes. And then, so behind the scene, it used TensorFlow, it applied each of the rows of some data, and then injected and then produced the new output out, and then gave it back to Spark. So here, as you saw, I didn't need to write some, apart from this description of the graph of computations, I didn't need to talk to TensorFlow, I didn't need to open sessions, deal with the hardware. This is all done automatically under the hood by this library. So of course, in order to be real, so the API looks pretty convenient. Now, of course, you're going to ask me, okay, this is all for the sake of performance. Is it really working as advertised? So you can implement that very easily by using the Python interface of Spark, by Spark, and the Python interface of TensorFlow. So you could simply embed these computations inside Spark by using the Python interface. But if you do that, you'll pay a big cost in communication. Because if you look at how Spark and Python communicate, they will start from, so the data will flow from Spark here to TensorFlow by first being represented in a compact manner inside Spark. Then it gets converted to a Java object. This Java object then converted to a Python pickle file, which is a Python way of serializing data. It gets sent through a network socket to Python. And then Python deserializes this data and then passes it to the C++ side of TensorFlow. And this is really inefficient to do. In fact, this is most of the time, if you do that, most of the time is going to be spent shuffling data back and forth between the Python and the Java side. So we can definitely do better than that. And TensorFrame essentially removes the Python layer around that. It directly embeds TensorFlow inside the Java virtual machine that is on the worker. And it is able to take the data represented by Spark, convert it to a Java row, and then pass all these rows to the C++ side, where then it is processed efficiently. So now there's no more Python in the picture here. Okay, so this is all very abstract. Let's talk a bit about some numbers. And let's talk here about one of the, for example, the problem of kernel density estimation. So in that case, you have a number of points, and you would like to build essentially a smoothed out representation of this distribution. So it is a non-parametric problem. There is usually there's no good way to pick one of the crucial parameters of how much smoothness you want to add, and that can be easily evaluated. So the function to evaluate it is this big math function here. So don't worry about the math. This is mostly to tell you that it is a big numerical function, and this function also is very good for to be vectorized in that case. So it is very easy to send different part of this computation across different machines. So here we have this big numerical function that we need to apply on each of the points. So if you are a Scala developer, you would say, no problem. I can use all the primitives of the math library of Scala. I can write a for loop, and I can translate this expression here, this sum. I can translate it into the Scala program. So it is fairly readable, it is fairly short, and it is going to give me the results, but it takes a certain time to compute. And if I have some Scala experts here in the room, they're probably thinking, this is not the right way to deal with that. Because here I'm using high-level constructs from Scala, such as map, and these constructs translate very poorly in terms of performance. So if you are a more advanced Scala user, you'll probably write something like this, which is less readable, but actually much better in terms of performance. Here I have enrolled the loops, and now the Java virtual machine can optimize many more operations under the hood. So that works. let's see what we can do if we use TensorFlow and TensorFrames. So this is the same code, where here, instead of using the Scala constructs, I'm writing everything into Python. And in Python, so I'm using the TensorFlow primitive for doing that. So you see the code is more compact, and it is as fast as the, or even actually slightly faster than the unrolled Scala code. So it is already better. And can we do even better than that? Yes. We can do one change to use GPU hardware on these machines here. And in that case, all I need to do is specify on my program, please use the GPU that is available on the machines. And behind the scenes, TensorFlow will use all that. So you don't need to do any of the, you don't need to add any more instructions. And because in this case, the problem is much amenable to these, to this kind of hardware, it goes much faster. So this is the kind of transform that you can do with, by using TensorFlow and writing it onto Spark. Instead of writing a Scala program that is fairly slow, you can rewrite this into a language which is much closer to what you use as a data scientist, which is Python. And behind the scene, the combination of Spark and TensorFlow will take care of distributing the program, executing it onto all the points inside Spark, and it will take care of most of the performance details for you. So, and after that, of course, since this is using a deep learning framework, you can do a lot more fancy operation than simply multiplications and sums. And one thing you can do, for example, is use all the deep learning operators that are available inside TensorFlow and directly inside Spark. So as a small example here, I have this demonstration called Deep Dreams, which essentially works in the following way. It takes a neural network, and it applies this neural network on pieces of an image. And for each of the pieces of the image, this neural network will say, this is a cat, or this is a dog, or something else. And and then after doing that, after detecting what is inside this image, or detecting some interesting shapes, then this program will reinforce the signal. So if it saw a square or round somewhere, it will have to reinforce the squareness of this part of the image. So if we look, so let's take so I took here an image from the place we are in here right now, in the convention center. And let's see, so, and then you can do a lot of very fun transformation with it using a neural network. And I think this is what it could probably look like once you drink a couple of beers here. So it's going to run for a few seconds. In the meantime, let me explain a bit what is happening here. So I'm taking a data frame containing some parts of the image. So I'm chunking the image. And then I'm applying this complex transform in the TensorFlow side. And this is all being done automatically by TensorFrames, so I don't need to care about the details of communicating a big neural network onto the machines. It is all automated. So let's see if it gives me something. So here, each of the iteration corresponds to essentially taking the image and trying to reinforce the signal it sees inside the image. And eventually, so then you can really build some easy and cheap art like that. So if you want to be a famous abstract artist, it is very easy like this to build in a matter of minutes some interesting art combining deep learning and Spark. So here, if I were to run the same demo on just using one machine, then it would take about 30 minutes to 40 minutes to generate the same image. So here you can see how we use all the scalability and the power of Spark under the hood to get quickly some results without having to care too much about optimizing these workflows. Spark takes care of all the details of spreading this numerical computation for us. Would you mind holding for your question? I think we'll have a microphone at the Okay, so what else what can we do to improve things even further? As I was mentioning in this program here, in this slide here, there is still this, this conversion between the efficient packed representation done by Spark for the data, first into a Java object, and then it is being sent to, on the other side, to TensorFlow. So of course, what we like to do is to remove the intermediate Java representation. And this is work in progress. It works for simple objects, but it's not there for everything yet. And eventually, also TensorFlow allows us to, because it is written in C++, it allows us to directly take to point at some data without having to copy it first. And this requires more cooperation from Spark so that it doesn't try to move the memory, but then it could lead to some potential improvements too. And finally, for now, since Spark works still on a row-by-row basis inside its engine, but TensorFlow and a lot of other frameworks really like when the data is already in a compact form. And there is some work to add columnar storage representation of the data directly inside Spark, which would speed up a lot of these numerical use cases like this. So yeah, so we'd like to add more integration with Tungsten. And also, for now, it doesn't support natively the MLlib data types. It can read inside the MLlib data types. It can see what is inside the vectors, but it cannot directly understand that you have a vector here. So that's something that we'd like to add as well. So to recap, we all know how Spark can be used for doing distributed computing on thousands of computers. And combining it with TensorFlow, which is really something you can think of as being a high-performance numerical framework, allows you then to get really the best of both worlds. Because you can have a simple API to express your numerical computing problems, and then you can distribute and leverage the hardware on your cluster without to worry about all the distributed aspects. So you can try all these demos, and we have also a couple of other demos available on the documentation there. So thank you for your attention, and I will be happy to take some other questions.
We have two mics on either side of the aisle. Do you mind actually just walking up to the mic and answer your questions so we can actually catch the questions on the recording? There's a mic right here in the front, and there's a mic right here. Do you mind? We'll take a few about 5 minutes Q&A, and then we'll go on to the next one. The two mics on either side of the aisle, please do queue up for the question.
Okay, so hi. I have a question. How do you even get these images to be data frames?
So yeah, how do the images get into their frames? So there are a couple of ways you can do that. Actually, so in this case, the data frame contains patches of images, and each of these patches is just the list of pixels. So from the perspective of Spark, it doesn't even know there is an image. All it is a list of integers representing the raw value of the pixels. Actually, speaking about images, tomorrow during we're going to have a deep dive on deep learning pipelines, which is one of the libraries that allows you to also deal with images inside Spark. So we'll have actually a much more thorough answer for that tomorrow afternoon.
Thank you.
Over there, next one.
Yes.
So 2 questions. I'm sorry. The first one is, can we teach neural network with a framework or not yet? And the second one is, do you load the full partition into the GPU or row by row? I didn't get it.
Yes. So your first question is really, can it be used for training on top of also being used for batch processing and inference? Yeah. So in this case, this framework is really meant to be applied as a single stateless function. So it is really working well if you want to use if you just want to do batch inference. That being said, it supports variables. So for a simple case, you can for simple cases, you can keep intermediate results inside the memory of each of the workers in TensorFlow, and then retrieve it at the end of your computations. This is not as easy to use as, of course, dist, keras, and all the other libraries. So for your second question as to whether it works on rows or on something more complex, you actually have 2 APIs. One of them allows you to work row by row, and the other one allows you to pack a number of rows together so that you can run more computation at the same time and be more efficient when you talk to TensorFlow. So you can have both for that, and the wiki actually of TensorFrames contains some examples for doing that.
Hi, thanks for the talk, very interesting. I was actually wondering how, because you skip these Python pickling parts when you implement the TensorFrames, but then in the examples, I guess you use Apache Spark to call it. So why can't you do it directly from Scala as well? Or can you? Actually?
For the image example?
Yeah.
Yes, well, mostly for the image example, you could write everything in Scala. And actually, you can write even the neural network graph already in Scala if you want to. It's a bit tedious to do, but it is possible, for example, using TensorFlow Scala. Mostly for ease of display and representation here at Python. But the Python side is just used for the visualization and for building the first graph. After that, from the Spark's perspective, it doesn't see Python at all anymore. So it would actually translate the same. It actually first translate into Scala and then into a TensorFlow primitive for that.
Go ahead.
I wonder in Databricks, what kind of GPU instance you are using inside the Databricks? And the second question is, how can I use the multiple GPU instance, multiple GPU in Databricks?
Oh, so this question is very Databricks specific, but I can certainly answer it. So Databricks supports all of the AWS GPUs, so the KIT family. And also, behind the scene here, for example, in this example, it uses distributed GPUs onto a cluster. So if you want more details, I will be happy to chat with you after that.
Okay, so there's I only could use the Amazon Web Server GPU instance in Databricks. I can't using some come from Google Cloud or some from Azure. Is that true?
No, so you can only use AWS GPUs for that.
Okay, so about the kind of GPU cluster management, so is there any kind of console or kind of the portal I can check out?
Yeah, so the number of metrics and other information available, but let's chat offline about that.
No problem, thank you.
Yeah. Final question.
In a normal Spark, when you have a mapping between CPU cores and tasks, and you might have several executors per machine, if you have a single GPU per machine, is there any similar sort of considerations, or is it all the executors fighting for the CPU at the same time?
Yeah, that's a very good question. So how does the mapping happen between the tasks and the hardware? So you have different strategies for doing that. If you use Yarn, for example, Yarn has an understanding of the GPUs, and it knows, so it is able to pin a specific task to a specific GPUs. If you use an environment like Databricks, for example, in this case, since the scheduler doesn't have any notion of and since Spark doesn't have any notion of GPUs, it actually executes only one task at a time on each of the nodes. So essentially, it says the number of CPUs in this case is equal to 1. But then TensorFlow under the hood is able to use and leverage all the hardware and run using the multiple processors and multiple GPUs if you program it so. So there's definitely some interesting question of user experience here.
Well, give a big hand to Tim Hunter, guys. Here to come back. There's going to be plenty of beer after the meetup. We'll have another networking session. So unless you're really thirsty or an alcoholic, they will make an exception. But do come back because we have a long night. Okay, today, I mean, if you were to go to any big data conference on machine learning, is an incredible trend that has really taken off. And you might ask why? Why is it machine learning has really taken off so quickly in such a short amount of time? And my contention would be that we've actually made immense strides in distributed computing. Not only the fact that the frameworks and the algorithms are more efficient, but the fact that we can actually handle large amounts of data, and as a result, we can actually predict with reasonable amount of confidence what our predictions are. And we also have the ability within Apache Spark to build very complex machine learning pipelines with Spark. And today, Holden is going to talk about how to construct ML machine learning pipelines. A little bit about Holden. She's actually a good friend, employee from early days of Databricks. She is an international global trotter. I really literally mean, I don't know what she eats for breakfast, but she's London in one day, Copenhagen in next, Cape Town, South Africa, third day, Bombay giving conferences, talks, holds office hours at the cafes. And when she's not traveling and speaking and writing books, she's also working at IBM as a software engineer and feverishly contributing to MLlib and PySpark. So please, warm welcome to Holden from IBM.
Thank you for that wonderful intro. It perhaps oversells a bit about what we're going to do tonight. So I hope you can all lower your expectations back down to something that I'm actually going to be able to accomplish in the time that we have. So let's go ahead and drag my slides over. Can we switch over to the, yay! Okay, now I can see where I am. Rockin'. Okay. So this very tasteful loading screen. And we will just go ahead and disable my Wi-Fi so it prevents from cache instead. And there we go. Present. Rockin'. Okay, so yeah, introduction to Spark ML, machine learning at scale. The examples tonight are going to be in Python and Scala. I have no idea how to do any of this in R, but I'm sure it's doable, probably, I hope. Oh, okay, I'm getting some shaking heads. Never mind, if you use R, good luck. So my name is Holden. My preferred pronouns are she or her. The rest of this has already been very nicely introduced. I'm a co-author of many Spark books. I have one from my publisher that I can give away to the first person to ask a question during the timed question period. I get much better royalties on this one, so if you don't get the free one, I encourage everyone to buy several copies of it. In addition to like who I am in the Spark community, outside of Spark, I'm trans, I'm queer, I'm Canadian, which is perhaps not the biggest surprise in Europe, and I'm part of the leather community. And it's just, we write the same shitty code, right? We all get the out-of-memory exceptions in Spark. There's no secret Canadian garbage collector that we've been hiding from you. G1GC is pretty good. And if we work together, rather than like spending our time yelling at each other for being from different backgrounds, we can finish our code faster, and I can get to go home and see my partner, and you can too. So just like be nice to your colleagues and coworkers. Hopefully that's okay with people. This is the mandatory slide from my employer. My boss is not here, and so this continues the trend of I really don't know what to say about this, but he does insist that this slide is in every one of my talks. So if you're thinking about buying IBM, think of our nice, lovely green-colored lobby. It's the same color as a passing Travis build, and if you want to buy something, you want to buy it from a company with a lobby with a lot of green in it. more seriously, I'm at a technology center in San Francisco. I really like it. We work on open source code. A bunch of my coworkers work on Spark, but some of them also work on other Spark-related things. Yeah, bye IBM. Okay, my co-presenter today is Boo. She's right here. She also uses she, her pronouns. She is the co-author of Learning to Bark and High Performance Barking. You can follow her on Twitter at BooProgrammer. She has done a lot of barking at the latest Spark release, and so she is the reason why this Spark release is coming out. So I'm going to explore some of my assumptions about who you all are. We're going to talk about why there's two different Spark ML APIs. It's awkward, though, because the people that made them are in the room to some degree, and normally I take a few cheap shots at them, but yeah. Okay, I'm getting a thumbs up, so I can still take those cheap shots. That's lovely. I'm going to skip this code gen thing because we don't have a lot of time. I'm going to end up with some final optional exercises. If you are really enthusiastic about doing machine learning in Spark, there's some notebooks that you can go and load into your favorite cloud provider. I recommend IBM Cloud. Or realistically, you can load it into Databricks. And we'll talk about model save load and serving. So we're going to focus just on Spark ML today. As you probably know, since you're at a Spark conference, there's a lot of other pieces of Spark. The slide also serves to illustrate the fact that I do not have any graphic designers who work with me. While there are graphic designers at IBM, they do not deign to touch my slides. So yeah, we're going to focus on Spark ML and Apache Spark, and we'll also briefly touch on some of the community packages. So you've been laughing at some of my crappy jokes, so that's pretty good. So you're probably nice people, or at least sufficiently lubricated from the beer to be nice enough. I'm really curious, how many people are completely new to Apache Spark? Is there any? Oh, wow. Cool. There's a good collection of people here. So if after tonight's meetup you're like, what the hell was all of this shit? I recommend one of my books, Learning Spark, but also, more seriously, Paco Nathan has this really wonderful free online video. It's a little out of date, but I think it's one of the better introductions to Spark that's available for $0, and you should definitely check it out, in addition to, of course, buying my book. That one's the most important part. Are there any people who are diehard R users in the house tonight? Okay, well, for you, I'm sorry. Maybe you can fix all of these bugs and make it work in R. I'll introduce you to the R people. If you want to follow along with the notebook, you're going to need Spark 2 or higher. There's some exercises interspersed in my slides. Don't feel like you have to bust out your laptop and start doing them. Of course, feel free to if I'm really boring. So the main one that you want is this really long GitHub link, the only link that I did not bother to put a URL shortener on because I'm lazy. That's the one where you can go and find the notebook. It's in Python and Scala. And the rest of them are just general Spark resources that you'll probably find useful. Today we're going to use some genuine kilobytes of data, mostly because I want people to be able to run this on their laptop, because conference Wi-Fi and cloud-based notebook providers is an ambitious goal, although I appreciate demos done in cloud notebooks at conferences. I just would never do it myself. Yeah, cool. So the two Spark ML APIs, there's Spark ML lib and there's Spark ML. And Spark ML lib is a really great thing. It has a lot of wonderful tools to do machine learning, but it doesn't have a lot of really wonderful tools to do data prep. And there's this really unfortunate thing that when we get out of the world of toy data sets, our data tends to be messy, right? Almost all of the time, we spend more time doing our data prep, data cleaning, and feature engineering than we do playing around with different cool, exciting algorithms. So the Spark ML lib API just really was built with cool algorithms and maybe not as much good data prep tools. At least Tim is distracted, so I don't have to worry about him getting too upset. But the pipeline API is wonderful because it looks at scikit-learn and says, ooh, those were some really good ideas. What about if I made an integrated environment for people to do all of their feature prep and data cleaning in a single place, right? And so that's the one we're going to focus on today. If you've got some old legacy code using Spark MLlib, that's okay. It's not going to be having a lot of new features developed into it. Those are all going to Spark ML and other fancy community packages. And you should probably migrate, but you don't have to migrate today. And so here is a really simple Spark ML pipeline. And we can see that these stages are colored 2 different colors. The blue ones are transformers, and transformers, while being a really cool name, are actually the simpler ones. And so transformers just take in data, and they produce results immediately. And estimators, while having a less cool name than transformers, actually are the kind of fancier ones. They're the ones that have to see some data and be fit on it. So naive Bayes is a classic example of an estimator. The string indexer is one which we don't necessarily think of as an estimator as often, but it's, since it has to see all of the strings that are present in a given field to create the mapping, it's actually an estimator. So estimators aren't limited to machine learning models. You can have estimators for things that are in your feature prep stages as well. Interestingly enough, a Spark ML pipeline is actually an estimator itself. So you can make a pipeline of pipelines. Please don't. It's I can put a turtle inside of a turtle, but the turtle's going to be kind of pissed off at the end of the day, so don't do it. Right, and so the thing with Spark ML pipelines is I can put all of these wonderful things together, and then I can call fit, and Spark will fit this for me. And so yeah, estimators have these functions called fit on side of them. Transformers, they just directly transform the data, and both of these have to provide transform schema, unless we're working in Python, in which case we got lazy. And transform schema is really useful, because, oh dear, this is really awkward. Well, okay, I like to say we fucked up and we didn't put any types on the machine learning stuff. Some people think it was an intentional good design decision. We can debate this over Bud Light Lime or Guinness as appropriate. But transform schema is sort of this realization that failing machine learning jobs in hour 23 of a 24-hour job is kind of a shitty experience. And the idea is, while we might not have compile time type checking for the types involved in our machine learning pipelines, at the very least, we can do runtime type checking before we do all of our fancy work, right? So I fail in hour number 1 rather than 23, and it's not compile time, but it's still pretty okay. Not a guarantee, things occasionally go sideways by a support contract. And also, our pipeline stages have parameters for configuration. And this is really important as someone who works on machine learning pipelines. If I don't provide parameters for configuration, when your machine learning task fails, it's my fault. But when I give you enough knobs to control, then it's your fault when it fails, because you set the knobs wrong. The other useful thing is, realistically, you actually want to configure a lot of these. It's not just for the purposes of me shifting blame as a library author to users. You actually do want to control your regularization parameters and tree depth and things like this. So how do we go from our estimator into a transformer? So when an estimator loves some data very much, they get a cluster together. And depending on sort of, the size of the data, how the estimator is feeling, is it a really complex one, or is it a little more simple, they spend somewhere from a few minutes to a few days, normally in the span of a few hours, just hanging out on that cluster, getting to know each other. And then after they've really gotten to know each other, the wonderful stork, in this case the Spark driver, will come and deliver a nice baby transformer. And the transformer is clean and happy, and it's ready to predict results for us. Normally, this gets more jokes. I guess the stork thing isn't as popular over here for explaining computer science terms. I assure you, definitely a real thing people do in America. But essentially, you can just assume there's this function called fit. Inside of it, some magic happens. Don't ask a lot of questions. If you find yourself looking inside of what happens inside of the fit function, that is the path to madness, or my talk on Thursday. And so, call fit, you get a transformer back, and we can predict some data. So we know that we've got some estimators, and I want to make some transformers, so I have to get some data for the estimator to, get comfortable with. I'm gonna load some really simple CSV data because I'm pretty lazy. Also because depressingly, I occasionally find big data in CSV format. At least it's not JSON. Or XML, oh God. So thankfully, data frame readers, you might be familiar with this if you were at the last Spark Summit. They're really lovely and convenient, and they support a wide number of formats, including Parquet, JDBC, JSON. And pretty much whoever wants to sell you something will almost certainly provide a connector to Spark. So take your insert favorite vendor name here and specify format as like com.vendorname.whatever thing it is they tried to sell you. And if it doesn't load, like, don't buy that shit. All right, okay, so loading some CSV data, pretty simple. I'm just gonna infer the schema because types are hard. Computers sometimes get it close enough to write. Nice, on like a little bit of a side note, it can actually do schema inference on JSON data, which is like super impressive and really awesome. On CSV data, not really as cool to be able to like look at that header row, but you know, it's cool. The same code in Scala, except I changed the delimiter for some reason, I don't know. Whatever, it's all the same. So we've done our data loading. Now we're gonna do our data preparation. But since this is like a talk rather than an actual solution to any of your problems, we're gonna do really simple data preparation. So as was alluded to, right now Spark's machine learning pipelines only really support doubles. There's some wonderful work from Tim and some folks at Microsoft and some other people to support more data types in Spark ML pipelines. And I am very excited to see that code get merged. And I don't think it's been merged yet, right? No, okay, yeah, I'm really excited to see this come, and we'll support like other data formats like raw images, but for now, we need to take our stuff and turn it into a bunch of doubles. If this was like a real problem that you were trying to actually solve for your business instead of just like screwing around on the internet, you'd probably spend a lot of time here, but since we're kind of just screwing around, it's a Meetup talk, we're just gonna go ahead and build the world's simplest data preparation stage. In this case, I've got some census data about income in America, which that is a whole big topic that you do not want to delve too deeply into. So I'm only going to use age and education numbers as my inputs to my model, because I don't want to learn anything that would make me feel uncomfortable. And my output column is going to be features. And then I've got some categorical information, but unfortunately, the category is represented as strings, even though it's income information. And that's okay. So I'm just going to go ahead, take my categories, and turn them into this category index. And now I can make a pipeline. Yay, a pipeline. It doesn't do anything useful yet, really, but it does our data prep. So we've got this pipeline of data preparation. And we can do the same thing in Scala. It takes slightly less lines. Actually, mostly just because I didn't write comments in my Scala code. Just like my real Scala code. And moving on, so this pipeline has each of the components either has fit or transform. In this case, even though we're not doing fancy machine learning, the string indexer has a fit function because it has to see all of the different strings to map them to unique indexes. And so when I call pipeline.fit, Spark will go through, it will copy the transformer stages over, and it will then fit any of the estimators that have to be fit. And during this, before it's actually like fitting the individual estimators, it'll go through and call transform schema on this input data frame at each stage to make sure that the data types actually line up. Unless you do this in Python, in which case we'll just fail in hour 23 of your 24-hour job. So if you use Python, please make a really small like sample first and run it through. Otherwise, you could be a very sad panda. Unless you're running on IBM Cloud, then I get paid by the hour, and like that's pretty cool. So we've got a really simple pipeline: input data, assembler, and then string indexer. And this leads me to like a little side point. Is you can see each of these stages add data, and none of them really take away any data. And this is pretty good, because we might want to actually produce multiple synthetic features from the same input feature, right? Like I might have information about if you like cats or dogs, and I might actually want to encode that as 2 separate Booleans. And then if I threw away my input data after I encoded the first time, I'd be sad. The only downside is sometimes you can get really big rows if you're creating a lot of synthetic interaction features. And so you should come to my talk on Thursday to learn how to write a custom stage to throw away the pieces of data you no longer need. Or you can rely on Spark's optimizer to not copy those around, but yeah, good luck on that. So now we're going to train a really simple model. And I'm going to train a decision tree classifier because I'm not trying to raise money in VC capital. But we'll have a slide on your deep learning options for later if you're trying to raise some Series B rounds. And here we say our label column is category index. This is our features, we fit it, and this gives us back a decision tree model, right? And we can use this to predict things about people. On the other hand, though, this isn't very useful because I told you there were these pipelines and we could make everything integrated, and I trained this other thing afterwards. But it's okay, so we can just go ahead and I can take my previous pipeline and I can just reconstruct it and put the decision tree on the end of it. And this is really cool because if I want to try out a bunch of different models, I can just swap them in on the end of my pipeline and see how they perform. Pretty much the same thing in Scala, different colors from the syntax highlighter. Yay. Yay! You have an ML pipeline. If you were in San Francisco, this would be enough to close your Series A. You probably would want to go to Stanford for a year and drop out first, but yeah, cool. And now we're going to predict something on it. And this is the sort of inconvenient part. After you've trained your machine learning pipeline, before you raise your Series B, they actually want to see predictions from your pipeline. It's okay, you don't have to do that for your Series A though. But it's really convenient because all of my feature prep stages are encoded in the same pipeline, so when I have new records coming in, I can just take my pipeline and transform them, and all of the feature preparation that I need to do will be applied. That's pretty cool. Exercise 1, if you're interested in this, you can read it later. Another thing that you can do if you actually want to see if your machine learning jobs are at all useful is Spark has built-in tools like cross-validation. And you can test your model performance because remembering to save a test set is kind of hard, and I'm pretty lazy. On the other hand, if you're the kind of person who maybe didn't do super well in statistics and your boss is like, yeah, we are now a deep learning company or an AI startup, and you have to make this shit work, you might be like, there's a lot of parameters to tune. I don't know what the fuck these are. And that's okay. You can use parameter grid search to try and figure out some reasonable parameters. And if you just never show anyone your cluster logs, you'll be fine. So you can just go ahead and you can have Spark automatically fit these parameters using cross-validation and the parameter grid search. If you do this, please save a test set beforehand. Otherwise, yeah, your results are going to be just delightful. Essentially, cross-validation because thinking is hard. And you might be going, Holden, decision trees are not enough for me to raise money on. I need a random forest at least, and that's okay. We have a lot of different models that are built into Spark, and in addition to the models that are built into Spark, there's other fancy models made by people who have either way too much time on their hand or are very successful at convincing their boss that it's really important that they get 3 months to implement some really high-quality business logic. Then they go ahead and read some Fortran code from the 70s or 80s and re-implement it in Spark. And yay! So yeah, so there's a bunch of different things that are provided by the community, also known as people who are not, well, actually some of them are Spark committers as well. But essentially, things which might not meet the bar of being included in Spark, but are still totally good enough for you to run in production. Notably, if you're a publicly traded company, send me your ticker symbol, but not in email, because then the SEC finds it. So XGBoost, Feature Hasher, there's even fancy deep learning things that implement the Spark ML API. They'll be a lot more useful once we support additional data types, so I'm really looking forward to that. But if you need to go and raise some money in Silicon Valley, you can use DL4J in this, and you can actually just swap in this decision tree with DL for J and go raise a shit ton of money. I mean, that's my understanding of venture capital. Yeah, cool. And so now we get to this awkward question. And this awkward question is, how do I serve my results? And so if you're lucky, your boss doesn't pay a lot of attention to what's going on, and they're okay with just batch serving, right? They're fine with you giving people results tomorrow. On the other hand, your boss might have also caught on to the industry's trend of everything is streaming now, which is a delightful industry trend, except for the slight problem of it gives me like really much harder real-time guarantees to meet, and I don't like that. So in batch mode, you can just use Spark's built-in sort of formats. On the other hand, if you want to serve real data in like latencies that are acceptable for like a web browser or something like that, you are not going to want to route all of your requests through your Spark cluster, right? That is not going to be a good time. And in that case, some of Spark's models support PMML. Notably, none of them in the Spark ML pipelines do. Really sorry about that. I have a pull request I've been meaning to get back to. I'm totally going to bug Nick to review it tomorrow. It's probably not going to be merged by Thursday, though. On the other hand, a really common approach that people do to solve this is they find another team inside of their organization which already has to serve a machine learning model, and then they figure out whatever format that is, no matter how insane it is, and they just export to that format and make serving their problem this other team's problem. And so I encourage you to do that because I like making problems other people's problems. The only problem is if you're at a startup, there's a chance that the other team might also be you. And then that's just kind of shitty. And in that case, there's a bunch of libraries you can try. I have opinions about a lot of them, but this talk is being recorded, so I'll save those opinions to myself. But try them and see if they fit your use cases. My suspicion is you will end up writing a lot of really lovely high-performance Scala code. Right, and now we get to the second most important slide, which is there are a lot of really wonderful books on Spark. Some of these I did not write. Those books are still lovely. However, I do get the highest royalties for high-performance Spark, and so that is the most lovely book. For people who are completely new to Spark, thank you for coming. I'm really excited you're here. I think learning Spark is pretty good, but I'm pretty biased as I'm one of the co-authors. I think learning PySpark for Python users is a really wonderful resource. I am not one of the co-authors. I did review it though, and Denny gave me a lift to the airport in Seattle, so like, some amount of bias in that department, but not nearly as much bias as this one. Buying a copy of High Performance Spark will provide a struggling engineer a quarter of a cup of coffee. You too can help an engineer from turning to a life of enterprise support contracts. Okay, that normally gets more laughs, but honestly, if you have a corporate expense account, I think this is a pretty good sort of like what's next in Spark. It's not a great intro book, and it does get me a quarter of a cup of coffee. Yeah, cool. I will be at Spark Summit tomorrow and the next day. I'm talking on extending Spark ML, so how to implement custom algorithms that implement this framework so that people can use them. And I'm also talking about testing, which if you're going to work in anything which indirectly impacts my life, and you're using Spark, please test your code. If you're just a publicly traded company that does evil things, I'm sort of ambivalent on whether or not you test your code. And I will be at a bunch of other places, mostly talking about Spark. In Australia, I will be talking about things other than Spark, but I mean, it's Melbourne. They've got really good coffee, I'm told. So that is pretty much it for me. I have to give a talk on Spark testing in 2 days. So I have this wonderful survey that if you care about Spark testing, you can fill out and tell me your opinions. And then they will be included in Thursday's talk. If no one fills out this survey, it'll be the same pie chart as last time. But that's pretty much it. And if anyone wants to be the first person to ask a question, there is this book.
You want the book?
Yes, you have to go up to the microphone. Okay.
Hello, thanks for the talk. First of all, then I want to ask, you already said you can load the prediction model to the as a JVM related, let's call say API. Instead of using Spark streaming for prediction, do you think that there is an somehow benchmark with the API related issues?
I'm not super sure I got that question. But so,
Okay, let me wrap the question again. You said you can load the prediction model. I mean the ML model if
Yeah.
you run an API on JVM.
Yeah.
For these purposes, I use the Spark streaming to take the data from a messaging queue, then make the prediction in the Spark streaming, then
Yeah.
write results to another queue, and then API takes the results from there.
Yeah.
If we take the Spark and the Spark dependencies to the API, do you have some benchmark for these?
Yeah, I don't have benchmarks for what happens when you run Spark in local mode in your API serving results. I have seen people do it, and they send me a lot of emails asking me why their performance is so slow, and my response is normally, I told you not to do that. But I guess we work at the same company, so fuck. And yeah, the performance is not great. But I don't know how not great it will be for you specifically, and I can't share our internal benchmarks. But I can tell you, it was not good. Do you want this book? Yeah. Here. Oh, no. If you want a signature, I'll sign it for you afterwards.
Yeah, go ahead, your turn.
Yeah, thanks for the talk. I saw the API using the datasets, which is a type-safe API of Spark.
Yeah.
So, and then you say that actually the API is not type-safe.
Right, so it takes in data sets, but it takes in data sets with the parameterized type as an underscore, so it's not actually type safe. There is some work by some wonderful people in San Francisco who now employ a bunch of my friends to make a type safe version of it, but it's not public yet. So there is something coming. But for now, we just don't have compile time type safety.
Okay.
I'm sorry.
And second question on this regard. So what is the drawback if using the type-safe API and just convert it to data frames? Would that be like a big penalty of the performance or?
No, so there's no real meaningful performance penalty. The main thing is just I'm a Scala developer to a large degree, and I enjoy compile time type checking. It makes me feel more confident about my shitty code. And so when I don't have compile time type checking, I get nervous. And if you're not that kind of person, that's great. Good luck, and may your cluster not crash.
Yeah, thanks.
One question. Can I ask?
Yeah,
As you know, Microsoft bought the Revolution R company, and now there is a new version of SQL Server 17. They have ML Server. In ML Server, they took all the API in R and rewrite them also in Python. You can choose which parallelism you can choose, and also the context of the data. You can take data to local computer training, and then do it all data. Tomorrow I come to my company, and then I want to work with my scientists. Should I work with Spark SQL, or a mail server, a Microsoft? What is the pro and cost in short?
You're asking a Ford dealer if you should buy a Ford. So, yeah, you should use Spark, but there's not another answer I can give you, right? Like, yeah. I'm sorry.
A final question. Final, that's it. Yeah, go ahead.
Hi. Hi, I'm glad you let the only woman who wanted to ask a question, so thank you. All right, so this might be a bit incendiary, and I may not have had enough beers for this, but for MLlib, I realized that the naive Bayes classifier doesn't really allow for us to fill in a likelihood function. So the default is a normal one, right? So do you have multinomial ones or I guess custom makeable ones, like for the zero inflated one? And second question is the mixed effects model, right? Do you have anything for that?
So, I mean, it's been a while since I actually looked at the naive base code internally. I'm pretty sure we don't support multi-class still. If it's a thing that you're like interested in though, I'm always trying to get people to do my work for free. And I don't know if that's like a thing you'd want to do, and we could talk with Nick, the three of us, about trying to implement that together in Spark if that's something you'd want to explore.
Yeah, sure, and for the mixed effects model too, I guess I'll talk to you tomorrow, is it?
Yeah, totally. I'll be around tonight and tomorrow. I'm pretty recognizable.
Okay, thank you.
Cool.
Guys, we're going to have lots of drinks after 30 minutes. Unless you're going to die of thirst. Okay, well, final speaker today. Now, you guys have actually heard about structured streaming since it was first introduced in Spark Apache 2.0. It has actually made quite a bit of strides as sort of a de facto high performance and high reliable structure streaming engine to do all kinds of stuff and uses all kinds of production. And today, Bill Chambers, who's our product manager and also the co-author with Matej Zaharia, the creator of Apache Spark, on the upcoming book called Spark, the Definitive Guide, which everything you want to know about Apache Spark 2.0 onwards is the book, that's the compendium coming up soon. And he's going to tell us about the structured streaming. What do you think about, what should you consider when you're running structured streaming in production? What are some of the criteria area, and what's the history of big data as well? So please give a warm welcome to Bill Chambers.
Thanks, Jules. Yeah, so as Jules has said, I'm going to talk to you about structured streaming in the cloud, really just any sort of streaming in the cloud, and what you kind of want to consider and why you want to consider those things. So to start off, just a general overview, I'll start off by introducing myself. I want to hear a little bit about you. Then I want to sort of take just sort of a little review of streamings or big data streaming, the historical context, right? And then talk a little bit about sort of my hypothesis for the future, and then some general evaluation criteria, and then structured streaming, obviously. So along those lines, as Jules had said, we're just about to finish up this book. It's been a massive undertaking. I don't know how Holden has written so many. It's unbelievable. But I'm also a product manager at Databricks, and I focus largely on structured streaming. And so I talk with a lot of customers that are just sort of evaluating streaming engines. And a lot of this talk is just going to be sort of communicating the things that I hear from them. Also about me, so I guess I wanted to talk a little bit about my biases, right? And my first one is that I originally studied history in undergrad, so I don't come from the sort of computer science cloth. And I also went to basically Silicon Valley's version of a library school. And so that's at the UC Berkeley of School of Information. And so I like to write a lot of things down, and I like to catalog information. And as I said, those really inform exactly what I'm going to be talking about in this talk. So I guess to kick it off with a quote, those who cannot remember the past are condemned to repeat it. And I'll probably repeat this so that you guys are not condemned to repeat the past. But a more contemporary way of putting it is do not study, right? And so that was me. So now I want to hear about you. So raise your hand if you're from or if you live in Dublin. Okay, handful, keep them up. And then what about Ireland in general? Okay, a couple more. Europe? All right. And then rest of the world. Okay. That's a good community representation. All right, great. So I'm going to assume some knowledge of big data. This is an overly technical talk, so there's nothing to really worry about. I'll assume some knowledge of Spark, but again, by show of hands, who's sort of running streaming in production? Okay, handful. And then who's sort of been looking at it, or it's like on your company's radar, it's something you kind of want to be doing? Okay, about the same. So I'll start off with, as I said, that incomplete history of big data. So I think things really started off with two Google papers, right? We have the Google file system and MapReduce. And these really laid the foundation for sort of modern day big data. And they were written in 2003 and 2004, respectively, by obviously very intelligent people. And these really kicked off, how we approach big data today, right? They're the total foundations for Hadoop, HDFS, and obviously MapReduce. And Hadoop came around just a couple of years later, right? And here we have Doug Cutting, and this is like Hadoop number 1. Who knows how many there are at this point. And I think basically this was all about generating a community to sort of really try and solve this sort of big data problem. But I think one interesting tale about this is that this didn't This came out the year before the iPhone came out. So this came out before even traditional big data problems, IoT, et cetera. We probably didn't even have, IoT as really a part of the conversation. And I think sort of what's kind of interesting here is that big data has really changed over the last 10 years. And you can look at this particular sort of marketing collateral, and there are a fair amount of tools that this suggests that you have to use, right? We have, 10-ish for data access. We've got some workflow stuff. We've got storage stuff. And I think really there's only one way to just sort of describe this. And the word that really came to mind was complex. And I'm not really just saying that to sort of take a jab or anything like that. It's literally the definition, consisting of many different and connected parts. And I think complexity is something that we should really try to avoid. Because big data is already really, really hard. It's a challenging thing, right? It's something to take multiple computers, tell them what to do, and have them do that repeatedly and consistently in a coordinated way is really difficult. And so I think one thing that is really consistent about Apache Spark and really consistent about Matei's vision for Apache Spark is that it makes big data processing simple. And that's like the sort of subtitle of the book. And that was the one that Matei had chosen because really Spark just tries to do two things, right? Provide a unified engine for complete data applications and high-level user-friendly APIs, right? You don't need 6 different tools to sort of be able to access data. You just need one tool, one general-purpose computing framework. So at this point, really what I want you to take away is that the history of big data is just a history of complexity. And I think one of the reasons for Spark's great and really just massive success, right? I mean, we have a ton of people here, and this is just a free meetup. We have 1,000 people that are going to be here for the next couple of days just to talk about this one thing, right? And I think Spark is so successful at that is because it's really built to just manage complexity. And so my hypothesis here, and sort of, I guess this has been a bit meandering, but the sort of future history of streaming, if you will resemble the history of big data. And what I mean by that is that we're going to have a lot of the similar patterns that we saw previously and applying them again. And so my evidence for that is pretty just facts, right? We're still working with big data. So big data applications, streaming big data applications, they're still going to have a lot of those sort of inherited problems, right? It's just a lot of, as I said, big data is just complex. We're also in the era where we're getting lots of architectures, right? You've got the Kappa architecture, you've got Lambda architecture, you've got, beta architecture, any number, you could Google it, and I'm sure you can find one, right? And then, obviously, there are a ton of potential tools, right? We've seen Kafka streams, Samza, Flink, Storm, Spark streaming, structured streaming, Apache Apex, the tools sort of keep going on, right? And I think that this is very representative of the previous pattern that we saw with Hadoop, right? There's sort of a core problem that people are really trying to solve, and there's a lot of smart people that are trying to solve that problem, right? And in this context, I really wanted to just provide some simple evaluation tools to help you do your job, right? I think that experimenting around, just sort of like Holden was saying, playing around on the internet is super fun, right? But when it comes time to actually select a tool and really invest in it or convince your boss that it's the way to go, there are some really key requirements. And I think the first one is eliminate complexity. And you should do that if only for the selfish reason that you won't get paged in the middle of the night when things start going haywire, and then you have to do, this forensic investigation to try and figure out what's going on. I think also there's so much complexity that you'll be dealing with already, right? You're going to have complex data sources that have their own sort of funky eventual consistency, partial consistency, whatever you want to say. You're going to have some that are sort of streaming only, et cetera. You're going to have sort of unique different types of data sources. You're also going to have a lot of complex use cases, right? I think Holden did a really great job revealing a lot of the complexity that comes up in the context of machine learning, right? It's just naturally a hard problem. And you could tell from the questions that people continue to struggle with it because putting something into production is really, really difficult already, right? And that was basically all of those questions. It's, hey, I could do it behind an API. I could try and integrate it with Spark Streaming. And I think that we're just going to hit those use cases actually being possible in sort of the coming years. And I think that thinking about where that's going to be going and trying to skate to where the puck is going is going to be a really important lesson. Also, I think there's going to be this sort of general unification, and you see other people talking about it too, of combining streaming and batch and interactive queries, right? I want to know about what's happening right now, not just last year. And then lastly, you're going to deal with a lot of complex data, right? I think IoT or general information data is generally messy. Again, just as Holden was elaborating upon, you're going to spend, if you're doing a lot of machine learning, a lot of your time just cleaning data. You're going to be doing the same exact thing, whether it's streaming or batch or static or flowing. And so I think in the context of all of that, right, just really trying to avoid complexity, I want to talk about structured streaming that was released GA last June. And is anybody using structured streaming? Okay, handful. Has anybody heard of structured streaming? Okay, fair amount. Has anybody not heard of structured streaming? Okay, also a fair amount. Cool, so I guess to just sort of take a very high level, Spark effectively had two streaming engines. And we saw that sort of a couple of slides ago. There's the dstream API, which is often referred to as Spark Streaming. And that's built off of RDDs. Okay? Those are the lower level sort of physical, still logical, but rather that's like a lower level API for data manipulation. Structured streaming is built off of Spark SQL. And so it takes that same sort of data frame API and is akin to the MLlib Spark ML that Holden was referring to, right? So it's sort of this next generation technology. And with that, structured streaming, surprise, surprise, doesn't really try to, or it wants to do it a lot, but it really wants to make it easy on the end user. And it's stream processing, as I said, built on Spark SQL's core engine. So it's fast, scalable, fault tolerant. It's battle tested by the millions of workloads that run Spark SQL or Spark structured API with datasets or data frames. And then it also wants to provide rich, unified high-level APIs so that you don't have to manage a bunch of sort of low-level ideas and low-level complexity that using can really become problematic, particularly in production. And so I think one thing that's sort of it's kind of the elephant in the room, if you will, that's not Hadoop, is that why does structured streaming exist anyways, right? Spark Streaming or the dstream API existed. And now it's like, hey, there's this cool new one, but it's like, well, why are we here in the first place, right? And Spark Streaming was really good at sort of what it did. And that was just sort of high volume, just move it along, right? Just kind of like Spark. But it really didn't allow for a lot of sort of the complex use cases that I was saying were going to come up in the requirements, right? Where you want to interact with streaming as well as batch. You want to maybe join offline and online data. You want to do windowing or sessionization, et cetera. The RDD API, frankly, or the dstream API, it just didn't do it, or it didn't do it very well. And I think that was, I know of some just absolutely massive use cases that are just built on dstreams. And I think a lot of companies put it in production, and I think that that's great. Like, I don't want to knock that. But I think, as I was saying, with skating to where the puck is going, it's just got to be easier, right? And reasoning about all sorts of, writing your own custom operators or streaming operators, or writing, your pipeline in streaming, or writing in a batch. Those are basically, batch or streaming is an implementation detail. And so structured streaming builds on a lot of the capabilities that didn't necessarily exist in the dstream API or Spark streaming. So it's end-to-end exactly once. That was sort of supported by both. But it really handles out of order and late data and just allows you to do that with SQL. Really easy. And it's got productive and simple APIs, right? I explained that in the beginning. Hey, my background was originally in history, and I taught myself a little bit about computers along the way. But in that context, this is something I really picked up and was productive with quickly. And that's one of the reasons why I really wanted to sort of help out on this project. And so in that, there's really no level streaming operators or APIs. You don't have to reason about sort of complex failure scenarios. And there's really no boilerplate code, which sort of comes up in the context of a lot of other frameworks. And so I think really the key takeaway for structured streaming and for dstreams, right? Dstreams, you have to think about streaming. You have to think about how sort of the data is going to flow through the system. With structured streaming, you don't have to. And as an end user, you shouldn't have to. That's like not really your job, right? We already went over that you already have enough to deal with messy data, with complex business use cases, and timelines, et cetera. And so structured streaming, the principle that it puts forward is just tables and streams, same thing. Just a sort of Spark SQL table is done. A structured streaming table is not. And so new data in the stream is just new rows in a table. And it really is that simple. And so you just write simple queries, and Spark continually updates the answer. And so the reason another reason this made me so excited is because, as I said, it's really easy to be productive, and it's really easy to put in production, especially if you already use Spark. And so, just to sort of take a look at what it kind of does under the hood, here we are reading. You'll notice that it's the data source API that Holden was talking about. And we specify our format. We specify a couple options, basically the same. The key difference is read stream. And that just says, hey, I want to do this continuously and update it along the way. We can perform any of our same sort of static or streaming data frame transformations. And then we'll write it out, just like we were doing before. And so that supports data frames, data sets, SQL. In that context, since this is still Spark SQL, plugs into the same engine, we'll go ahead and create our logical plan, our optimized physical plan after going through Catalyst. So we get to stand on really the shoulders of giants and use the same high-level APIs, but now it's continuous. And then Spark SQL, convert that to a batch-like query, and we'll do those automatic incremental updates for us. And that's just not something that we really see in any other system, right? Again, you shouldn't have to reason about streaming. That's not really the key value, right? The key value is to actually really deliver, get this use case into production and get your business running on it. And so, again, to just review why that's better, I think the unified engine is going to continue to be really, really important, right? I told you these are my biases, but I think if you look at the history of Hadoop and how Spark really, won big data, it's because of that unified engine. It's just really easy to use. And I think with what structured streaming really provides, that's really next level, is now how the code executes is just an implementation detail. It's the same business logic, batch or streaming. And then on top of that, they're really high-level, user-friendly APIs. It's a simple, flexible, general-purpose tool set. And I think, as I had said, a core goal as you go through, right, over the next couple of days, you're going to be talking to vendors, you're going to be talking to product managers or engineers, people that are really excited. But one thing I would urge you to keep in mind, if only for your sort of future self, is to try and eliminate complexity, right? Because that'll just make your job easier down the line, and you'll be able to trust in the things that you actually build. So look for systems that help you do that. And then I would also say those who cannot remember the past are also condemned, or are condemned to repeat it. And so that is the end of my talk. Thank you. sort of getting in between people in the pub here, so.
I know. Any questions? As somebody say, as Alan Kay said, you know, simple things should be simple and complex things should be possible. And I would add something from what he said, complex things should be eliminated. Go ahead.
So for my use case, I'm listening to a stream. Maybe it's like 200 gigabyte a day. And it's not a very stable stream. So sometimes it will peak at like 4 or 5 times. So in this case, will structured streaming, would that help with this situation? I know previous version of Spark does not support auto-scaling. And is this newer version would be better handling that situation?
Yeah, it's a great question. So I'll just sort of touch on a couple of key points. So the dstream API, sort of data was sort of more pushed through it as opposed to sort of pull-based. And that made it really hard with those big bursts of data, because then it could just sort of overwhelm it. But what structured streaming does is it works great with a tool. I'm assuming you're using like Kafka or Kinesis or something. Yeah, so Kafka's not just gonna like throw away the data right away, right? It keeps it all around for a little bit. And so what structured streaming will do is it'll try and process as much as it can, but in the context, it doesn't want to get overwhelmed. It wants to keep running. And so it'll sort of, you know, break it down into chunks, and then that helps even out those blips, right? So maybe even if you're using a smaller cluster of computers, which is great for sort of operational complexity, basically it'll try and do as much as it can, and then it'll play catch up when it cools down. Yeah. Next question.
Yeah, thanks a lot for the talk, and I have a question regarding the fault tolerance.
Yeah.
So the known problem for the Spark streaming and integration with Kafka is the consistency guarantees. So this at least once, at most once problems. So Kafka allows you to commit at the point you want. The confirmation of the receival of the message. So if the worker fails, it has to basically two options. Either it's committed after it read the message, or after it's already output the result of the computation. So how does structured streaming deal with this problem? So
yeah, so I mean, this one's fairly, I guess, low level, and I don't necessarily want to dive into the details because I don't necessarily really want to make a mistake about the detailed implementation on stage. But basically, structured streaming is designed to provide end-to-end exactly once guarantees. And so in that context, it builds upon the same fault tolerance that, you know, Spark's batch APIs do. It's basically the same engine, except do it incrementally as opposed to that. And so in the event of an executor failure or something like that, it already manages that, and all of that has like been really battle tested. It is dependent on the particular sync. And so I'd want to check into look into the code and talk to an engineer before I answer that definitively, but I'd be amazed if that wasn't handled.
Mm-hmm. Okay, thanks.
Just to elaborate on that, tomorrow TD is going to be giving a talk on deep dive in structured streaming. And we're going to go into the entire process of how checkpointing is done and how we actually maintain and honor the exactly one semantics, both for the reading from the string, reading from the sync, and also writing to the string. Okay, so hold on that question. Come to the TD's talk tomorrow, and you'll actually get all the answers that you want.
Okay, thanks a lot. Yeah. Thank you.
We'll take one final. Go ahead.
We got two. I'm going to just finish off.
From here. Go ahead.
Hi. So my impression as an outsider seems that this new iteration of the streaming API, one of the goals is to be more conformant to the Apache Beam model, where there is this idea of merging streaming and batching into one kind of concept and defining it in one way. So was that one of the goals? And in general, what do you think about the Beam model and their goal of kind of becoming the unified language of all streaming engines?
Yeah, that's a really great question. I think the guy who wrote a couple blog posts for O'Reilly, and I'm sure is behind Beam, I think he was behind like Millwheel and stuff like that, like the original streaming stuff at Google. Tyler Aikido, I believe his last name is, has some really great discussions on this topic, right? And I think that there may have been some inspiration from that, but if you think about really what Beam is trying to do, in my opinion, it tries to abstract those APIs even further, right? And they try and do it across engines. And the challenge with that, right, so they have like their connector for Flink, they've got their connector for Spark streaming, et cetera, right? And the problem with that is that each of those different engines has their own lag in terms of functionality that they've actually implemented, right? And so they have to do like the lowest common denominator across those engines to have something that's like widely supported. The thing is the Beam community, it's not like, thousands of people are just like, wow, I want to be a Beam contributor so bad. You know what I mean? Spark has so much energy behind it that it's funny. You just see lots of people contributing that were never contributing before. And so while I think like that general sort of API push is noble, and there's certainly some thematic elements there, I think with Spark, it's just done a little bit differently, and a lot differently, and that's because you really get that sort of unified end-to-end. It's not just, hey, slap on a new coat of paint and call it a day. Does that make sense?
We're going to take a final question.
Yeah, I got two questions. One is random question. So in the slide, you said you want to eliminate the complexity. So, but for the very beginning, you said for big data, you want to raise community. From the community, it means there's a variety in the community. So that caused complexity. So you also said you want to create a community, but you want to eliminate the complexity. How do you judge kind of those relationships? So the philosophy behind this Apache Spark is kind of more like the encourage community to create variety or eliminate, kind of block them.
Yeah.
So this is my first question. So.
Yeah, great question. So basically, in the context of community growth and sort of lots of flowers blooming, how do you manage sort of maintaining or eliminating complexity and stuff like that? And I think that that's where sort of community leadership is really, really important, right? I think one thing I was just saying to Jules before we got started, it's just an amazing group of people that have spoken here today, right? It's like totally different. None of us really have sort of consistent backgrounds. And I think that that's really good, right? But at the end of the day, you also need a strong sort of a vision and sort of guidance for where things are doing. And I think Spark's sort of vision for being that unified one computation tool, no matter what you're doing and no matter how you want it to run, that vision, I think, makes it so that everybody has to kind of conform to the community standards. And I think the Spark community has amazing standards. And so I think that helps kind of manage that tension. I mean, it's a great question, though. I mean, there's no like perfect answer.
I need a right from the very onset when
Mike Jules
actually came up, where Databricks actually started coming up with Apache Spark or donated Apache Spark to the community. They believed in the fundamental principle that innovation actually happens in collaboration, not in isolation. And using Bill's analogy about multiple flowers blooming, when spring comes in, the best flower will bloom and give its pollen that's actually identified by everyone. And that's the particular vision, that's the presence, that's the vision that Matei actually came up with, that we actually need to have a unified platform. Although all these different flowers gives you different flavor, but what if actually one flower that combines all these and gives you the same capability and the same fragrance and the same fertility, if you could use that particular term here. And that's the fruition of that. And I think all these different tools will actually emerge, and one that actually satisfies all the use cases across the board will emerge as the winner. So collaboration happens in innovation happens in collaboration, and that's one of the reasons why I think some of the tools will actually emerge yet, whether it's Beam, whether it's Apache Spark, whether it's something else. So I think in that note, we want to thank you and thank Bill again for giving a wonderful talk and give us a vision. And remember, tomorrow, Matei Zahari is going to be the keynote, so we got some surprises for you. So do come up, drink as many beers today, but make sure that you get up early in the morning and do come to the keynote. And you have 2 good days of Apache Spark. When you walk out from here, Spark will be tattooed under your eyelids. So thank you for coming tonight and enjoy yourself. I guess the beer is gone, but there are pubs around in lots of pubs around in Dublin, so hope to have a pint of Guinness. All right, cheers, guys.